Okay. So there's another step in actually converting a sample to a binary value. And so we've talked about sampling, ideal sampling, practical sampling. What we're heading for now is actually converting these samples into binary words. And there's this step that can often be ignored or overlooked, but it's important. It can be a source of error. Okay. And we need some way to quantify the error. But the assumption is at this point, when we've sampled an analog waveform, our sample has exactly the same value as the analog waveform. So if it's 5.23678 volts or whatever, that's exactly the value of, to infinite precision of our sample values. Okay. But with any sort of binary word, we have to choose a word size or sample size. It might be 8 bits. So with 8 bits, you can represent 256 different things. It might be 12 bits, so more different levels, 4096. Certainly, the longer the code word, the more bits you can have in the representation. So we're going to talk about this conversion of our sample values, exactly sampled values, into these discrete amplitudes. Now, you can think about this actually as converting an infinite precision array into an array that has finite precision. Okay, so I'm going to talk about. Let's talk about the input-output relationship here for our quantizer. So we typically have, I'm going to say, values between minus 0.5 and 0.5 are converted to 0. Okay. And values between 0.5, try to get the same distance, and 1.5 are converted to 1. Okay. And we only have a fixed set of allowable values in V of n. And similarly, values between 1.5 and 2.5 are going to be rounded to 2. And similarly, values between minus 1.5 and 0.5 would be rounded to minus 1. So this is the input-output relationship of our quantizer. So here, this would be, as I've drawn it, 5 level of quantization. And it would be designed for any input voltages between -2 and +2. Okay. But any value in that range is converted to one of 5 values. Okay. -2, -1, 0, 1, or 2. Okay. So, and to represent 5 values, we'd actually need 3 bits. Okay. So 2 bits, we can get 4 things. We need 3 bits to get 5, because with 3 bits, we can go up to 8. Now, typically, the number of levels here is a power of 2. Okay. So you normally wouldn't see a 5-level quantizer. They're just not, we'll talk about an error, but there's a lot of error here. So typically, you talk about an 8-bit quantizer, which would have 256 levels, or 12 bits, or 16-bit is CD quality. Okay. So, but I'm not going to draw 256 different levels. So what happens now based on this? Let's take a look at -2, 2, 1, 0, minus 1, minus 2. Let's say we've got some sort of waveform here that looks like this. And really my levels here are 1.5 to 2.5. Get rounded to 2 and 0.5. Anything there? And similarly here. Okay. Now I've got samples here of, I'll put dots here at my sample times. TS, TS, 2TS, 3TS, 4TS, and similarly back here, minus TS, minus 2TS. Okay. Now the dots here are what I'm calling my M of n values, okay, the exact values. Now in the quantization, these actually get rounded to the next level. So here, let's see, do I have them centered? No, I have them taking place. So this sample would actually get rounded to 1. Okay. And then this now is at 0. Okay. So I'll put a little x here, a little x here. This one is also rounded to 0. This one's rounded to 0. Okay. This one is rounded to 1. This one would also be at 1. Okay. We have drawn that one. It's also at 1. And then it comes back up. Okay. And then back here, let me do a couple more back here. That one would be there, but then it would be rounded to 2, kind of at the same point. So our analog waveform is this continuous curve, but our kind of quantized approximation to it, to 5 levels, is this stair-step looking thing. Okay. Again, the levels here are relatively large compared to what you would actually encounter, but the dots here are the M of n samples, and the x's are the Vn quantized values. QUANTIZED values. Okay. Now, the number of levels L is usually a power of 2. So L is 2 to the n. And we almost always refer to the number of bits, and that's the n value. An 8-bit quantizer would be 256 different levels. A 12-bit is 4096. A 16-bit is 65,000, whatever, 536 different levels in the quantizer. But you can see that quantization introduces error. I mean, once I've done this rounding, I don't know whether the original value, once I've rounded to 1, I don't know whether the original sample value, it could be anything between 1/2 and 1.5, right? In this particular case, the original value is 1/2, but once I've done that rounding, there's no way for me to recover the original sample value. It could be anywhere within that range. So the Mn is actually Vn plus En, where the term that's used for En, this error, it's called quantization noise. Sometimes quantization error, but often quantization noise. It's exactly as if, you know, at each sample point, there were noise present writing on top of, you know, the waveform I'm interested in that caused errors in my sampling. Okay. And what we're interested in is the signal to quantization noise level or ratio is reduced by using more levels. Okay. I'm just making that statement now. Hopefully you can kind of maybe see that intuitive. Here, if I've got 5 levels between -2 and 2, you know, I'm getting, you know, probably on error, half a volt error. If I've got 256 different levels though, my error is going to be considerably smaller over that same range. So one of the things we'll come up with in this chapter is actually a formula for the signal to quantization noise. Now this is always going to be present when and it's not the same as external noise, right? This is deliberately introduced in the sampling process. Before we come back to that, I want to talk about some other types of quantization. One is non-uniform quantization. Here I've shown uniform quantization, you know, with all my steps equally spaced. Okay. Seems like the reasonable thing to do. Why would you ever want to use non-uniform quantization? Well, the reason has to do with in audio, the ear tends to be more sensitive to smaller amplitude signals, lower volume signals, than larger amplitude signals. Okay, you can't detect the quantization noise as much, as easily. So this is, you know, a psychological effect or an acoustic effect at high amplitudes, as you can hearing the quantization error at low amplitudes. Okay. So someone had the bright idea is, well, what if I used if I use smaller levels for lower amplitudes, okay, and larger spacing at higher amplitudes? You know, so I still have my 256 levels, but they're much closer together at lower amplitudes than higher amplitudes. I can get better sounding audio. Okay. So we get improved performance, and this would be, you know, by subjective measures, by using closer quantization levels at low amplitudes. So the picture now would be more like this. Again, it's rather exaggerated. But the idea is I'm going to use smaller increments between my levels at lower amplitudes. Because now, you know, let's say this is 1/10 of a volt. At lower amplitudes, I'm not going to have, you know, I'm going to have less than well, if my step size here is 1/10, my error would be less than half of that, okay, or 50 millivolts. You know, here at the larger amplitudes, I can have larger errors, you know, maybe up 2-volt error up here, but again, the error is not as sensitive to those quantization errors at the higher volumes. So this is non-uniform quantization. Now, might think, well, this is probably a lot more difficult to implement, though, and it is than a uniform quantizer, but there are a couple of different tricks that are used. Instead of non-uniform quantizer, we can equivalently, you know, we talked about this, I think, last time. I could equivalently maybe amplify my low volume signals, okay, make them bigger, okay. Perhaps attenuate the higher amplitude signals, deliberately distort the signal, and run it through a uniform quantizer, and get the same effect as non-uniform quantization. Now that's distorting the signal, so at the receiver, I could undo the distortion though, you know, by applying the inverse operation, by then attenuating the low amplitude signals back so that they're back to their equivalent values. Okay, so we can run the signal through, it's called a compressor. It's nothing like an air compressor at all. It's really a circuit before sampling, and use a uniform quantizer. So the compressor amplifies low amplitudes. So often we'll talk about our signals having normalized amplitude between -1 and 1. So the negative portion of this curve would be, you know, the mirror image of this, but what a compressor curve would look like, something like this, okay? You know, where, you know, for an input value of 1/2, that gets mapped to a much larger amplitude of like maybe 0.75 there. Okay, so this is a typical compressor curve. This would be just linear amplification, which is often what you want. I mean, you make a big deal all through electronics on, you know, linear amplification, no distortion. Here we're deliberately distorting the signal to get better performance. We have to undo this, okay, to get back the original sound. That's done with an expander. Okay, that's the opposite circuit that we would use at the receiver. But, you know, we could use any sort of curve that has this general shape, and then use the inverse curve at the receiver to undo the distortion. So these are typical compressor I/O curves. Okay, and this is done by the telecommunication companies in the US. Actually, it's done all over the world. In the US, use what's called mu-law compression. Now, Now, what I'm talking about here is actually running this through an analog circuit, a nonlinear amplifier that does this before sampling. So we would run our original, actually analog filter, our analog signal through this compressor to amplify the low volumes, and then run it through a uniform sampler. There is another way that is not talked about in our textbook. You could actually sample using higher resolution, like 16 bits, and then convert that into 8 bits. So you can do it actually in the digital domain, using more samples again at the lower amplitudes than you do at the higher amplitudes. Yeah. You get better resolution at the lower volumes, yes. Not at the higher amplitudes. Yes. So this mu law compression curve, the sign of MT here is just to preserve. You'll see that the expression actually involves the absolute value. It's the log of 1 plus mu times the absolute value of the input over the log of 1 plus mu. Okay. And the sign just preserves the value of m. If it's negative, this result is negative. So what this curve looks like, the possibilities are, depends on mu. You get a straight line if mu is equal to 0, and then mu equals 255, which is typically used in the US. It's going to look like that. Okay. This is 0 to 1, MT and VT. And then, again, we use an expander at the receiver to remove the distortion. And this is done after we convert back to the analog signal. So in the US, talking about the traditional, what they call the POTS system, the plain old telephone system. So traditionally, you've had copper wire coming into your house, between your house and the nearest telephone exchange. Now, many, many years ago, decades ago, it used to be, copper from end to end, okay, or it was an analog transmission from end to end. Even, long distance calls were transmitted using analog. These days, it's primarily just analog to the exchange, where it's actually sampled and converted to digital. And then it may be sent over fiber optics or coax or microwave, any number of different transmission media. But before that sampling takes place, they do this mu law compression on the analog signal to increase so that you get better sound at the lower volumes. Now we got a bunch of different telephone companies in the US, so they all have to use the same standard. Okay, and that's this curve, because at the receiver, whatever final exchange you end up with, whatever regional telephone system that your endpoint call makes it to, they have to do the compression using the inverse curve, or the expansion using the inverse curve. Now in the US, they use this mu law compression. They use it in Japan also. I think in Europe, they use a slightly different curve. It's called A-law compression, capital A-law compression and expansion. But it's a common technique. Again, it's this same concept of introducing deliberate distortion at some point so that we get better performance in the presence of noise, or in this case, improving the subjective performance of our quantizer. Okay. I think I gave you a homework problem dealing a little bit more with this equation. But let's get back to the main topic here, pulse code modulation, or PCM. Again, this is probably the most prevalent form of modern digital communication. So in PCM, the discrete values from the quantizer are converted to code. I'll put down binary here, by an encoder. So this is really just converting these voltage levels, these quantized levels, to a binary number. Now, we'll see that there are a lot of examples in modern communication where the digital waveform is not necessarily binary. It might have 4 levels instead of 2, okay, or even 8 levels, or even 16 levels. So for 2 levels, you need essentially 2 pulse amplitudes, right? For 4 levels, 2 bits in a single pulse, you'd need 4 different amplitudes, right? If I used, I could do this, map this to a 0, and then no pulse to a 1. Alternatively, well, let me back, it's usually done like this. Alternatively, if I used 4 different levels, 4 different amplitudes, I could get 0, 0, 0, 1, 1, 0, and 1, 1. We'll see that my required bandwidth is proportional to my pulse width. Okay. The wider the pulse, the smaller the required bandwidth. It doesn't depend on the amplitude of the pulse at all, though. Okay. So by using 4 different amplitudes like this, I can get double the pulse rate. Okay. Now, I showed amplitudes here because that's the easiest thing to think about at this point. It could be, when we start talking about modulation, it could be 4 different frequencies that I use, that I'm switching between 4 different frequencies instead of 2 different frequencies, which would be the binary equivalent of FM, or 4 different phase angles, okay? Or perhaps if I used 8 different levels, I'm transmitting 3 bits in a single pulse, right? Or with 16 levels, or even in some cases, they've gone up to 256 different levels, phase angles, and amplitudes, so that you can transmit an entire byte of information in just a single pulse. Okay. So again, that's called M-level communication, capital M. So binary or 4-ary for 4 levels, or 8-ary are the terms that are terms that are used, but I can get much greater binary throughput by using M-ary communication. But we'll come back to that later. Right now, we're going to concentrate on just this binary encoding. And so my system kind of now looks like I have my original baseband signal, and I run this through an anti-alias filter. Remember, that's going to remove all frequencies above whatever I consider, if I'm sampling at 20 kilohertz, I want to remove everything above 10 kilohertz, right? Above half my sampling frequency, okay, so that I reduce the aliasing that occurs. And then I sample, and then I quantize this is the conversion to the voltage levels. And then I convert my levels. This is called encoding. Okay. And this is where I get my pulse code modulated output. At this point, I have, binary data. So this is a pulse code modulated transmitter. Now, the pulse code modulated data rate or binary rate is n times my sample rate. Makes intuitive sense. Okay. If I'm taking 1,000 samples per second, that's f of s, 1,000 hertz. But I'm converting each of those samples to an 8-bit word. I need to transmit 8,000 bits per second, right? So my binary rate is the number of bits in my sampler times the sample rate. Okay. And so this would be in bits per second is typically how that's written, BPS, or kilobits per second, or with modern communication systems, we're up in the megabits per second. Now, in the receiver, kind of a block diagram for my receiver, I have my data coming in. And at this point, I'm really still working at baseband. I haven't modulated this data at all. But this then goes through a regenerator, and I'll talk more about the regenerator in just a second, what the purpose of that is. But we'll typically have a regenerator at the receiver, and then a decoder to convert the binary words back into voltage levels, and then a low-pass filter, which is my reconstruction filter. And then I get back, an approximation to my original message. Okay. Yeah, the big advantage of digital systems over analog systems is really their noise immunity, or the fact that I can regenerate my binary signal. That regenerator is part of my receiver, but I can also have regenerators along the transmission path. Okay. Sometimes they're called regenerators, regenerative, or regenerative repeaters, or just repeaters can be used along the channel to eliminate distortion and noise. Okay. So the idea is, what I have after transmitting my nice, clean binary waveform, which you guys have probably seen on a scope, due to bandwidth limitations, due to the presence of noise. Let me kind of draw in, maybe, a long way away down the transmission line. This is the signal I get. Okay. Well, the idea is with a regenerator, what it will produce is now this nice, clean binary waveform from this noisy waveform that I get at the input to my regenerator. Now, the components of the regenerator is there's typically amplification or maybe some sort of equalization if I know that my channel introduces some sort of distortion. And then the other part of this is I'm just going to write it as a decision circuit. It's usually nothing more than a comparator, okay? You know, I will sample the waveform at these instances, okay, obtain the sample value, and compare that to, you know, maybe if I'm expecting 1 to be 4 volts and 0 to be 0 volts, and I'll compare it to a 2 volt level. So I'll sample it, just feed it to a comparator, but my comparator or decision maker, you know, I do need timing information in order to determine when I take these samples. Okay. That timing information is usually derived from the waveform. And again, that's something we'll talk more about. But here, I'm just making this decision at any point about whether the pulse is a 0 or a 1. So I just really recreate the binary pattern and then recreate the digital waveform. It's not like any sort of filtering of this thing to create the output. Okay. It's actually making this decision at each point, at each sample instant, about whether it's a 0 or 1, and then regenerating the waveform. Okay. Unfortunately, you can't do anything like this with an analog waveform. You don't know what's noise and what's not noise. Okay. Any sort of amplification is going to amplify the signal as well as the noise. With a binary waveform, you know it's only 2 possible values, 0 or 1. Now you might make mistakes, okay? There can be errors here. You know, a noise spike here when a 1 is present might take you below the threshold value. And then so instead of outputting a 1 here, I output a 0. That would be a bit error. So, you know, we can get bit errors occurring with regenerative repeaters. It really, the bit error rate depends on actually the signal noise ratio in the waveform. But regeneration gives digital communication systems a huge advantage over analog communication systems, which can't remove the noise or, you know, unknown types of distortion. But with a regenerator, I can completely regenerate, you know, this brand new digital waveform. And errors can occur. Are what we generally use as a quantitative measure of performance with analog systems is what we call the signal to noise ratio. With digital systems, instead, we use the bit error rate, you know, the number of bits that are wrong in 1,000 bits or the number of bits that are wrong in 1,000,000 bits. Okay. Now, the other thing that digital systems allow us to do is they allow us to transmit additional error correction codes or bytes that we can use to indicate whether or not an error occurred in the transmission. You know, something like a parity bit would be a simple thing on every binary word to make sure the parity is correct. Or another technique, another simple technique that's used with the internet is, you know, you take 1,000 bytes that you're going to transmit, you just sum them together as you're transmitting, and then after you get done with 1,000 bytes, you transmit that checksum byte. You know, the sum of those, you ignore the carries, you transmit the sum of those 1,000 bytes. Okay. At the receiver, it adds up the 1,000 bytes. Okay. computes a new checksum, and then compares that to the received checksum. Okay. If they don't match, we know that an error occurred. Okay. Now, a couple different ways of transmitting binary data. If you're transmitting computer files or something like that, then the receiver, after detecting that an error occurred, can request that the sending computer retransmit the data. Now, this is done with your downloads over your browser, over the internet all the time. It's done without you even knowing that it occurs. It's part of the protocol built into the internet, this transport control protocol. So, you know, it'll transmit a huge file. If errors are detected, it may request then that a portion of that file be retransmitted multiple times until it arrives, you know, essentially error-free. Now, if it happens in streaming audio or streaming video, typically don't care, right? If there's a glitch in the audio, there's a glitch in the audio, or if there's a, you know, pixel bad in the video or a section bad in the video, you know, it shows up as a corrupted section of the video, but it just goes on, okay? There's no retransmission. So streaming data is typically sent over the internet using a different method. It's called UDP, User Datagram Protocol, instead of TCP, Transmission Control Protocol. But again, another kind of advantage of using binary data is that we can add error correction into our binary data to make sure that it arrives error-free, something that you can't do with analog data. So, all right, that is it for today. Yep. Yeah, with no